Okay, so this is another style of differential equation that you see fairly often for what we call harmonic motion, when you have something that's swinging back and forth. This can be a wave on the surface of water, it can be an electromagnetic wave, it can be a swinging pendulum, it can be, in physics, a block on the end of a spring that's bouncing back and forth. They all tend to have differential equations that look like this, where you have the second derivative of their position and their actual position combined together. And we need to find a solution that will define this motion. Now, you might figure this out after battling with it for a long time, but there's kind of an established solution for this, which I'm going to tell you about. Because these things are described by waves, or oscillations of some sort, we expect them to be made up of sines and cosines somehow. The trouble is, we don't know if it's a sine or a cosine. If we knew it was a sine, we could write something like a sine a t, and that would be enough to define the motion. It's got a certain amplitude, it's got a certain frequency, and we could solve for those numbers. It could also be a cosine, and I'll use b cosine bt. So it could be a cosine that has an amplitude and some frequency of its own, and that could define the motion. And we don't know which one it is, and so what we do in general is we say it could be any combination of these things. So our s of t, we're going to say, is some combination of a sine function and a cosine function, and hopefully we'll be able to nail down which one it is. It might be some of each, that can happen, but in some cases you'll find that the amplitude of the sine is zero, meaning there isn't one, it's pure cosine. Or sometimes the amplitude of the cosine is zero, and that means your solution is pure sine. So we'll see which one it is in this case. If this is our original function, and could we find derivatives out of there? Probably. What would the derivative of this thing be? The a is a constant, so that derivative just goes through that. The derivative of sine is cosine at, and then the chain rule says now do the derivative of what's inside this. T is a variable, so that just disappears, and we're left with little a. I apologize for having capital A's and little a's. I hope that doesn't get too annoying. I'll try to say big A and little a if there's any ambiguity there. For the cosine, a similar thing happens. The derivative goes right through the big B. The derivative of cosine is negative sine, and then we get little bt. And then we do the derivative of little bt, which is simply little b, because little b is a constant and t is our variable. This is just like if you had 6t, the derivative of it would be just 6. So if we clean that up, we get s prime of t is big A little a cosine at plus, sorry, minus big B little b sine little bt. Not gorgeous, but that's all right. We can work with it. Now, this equation is about the second derivative, so we get to do one more step of this. At least these derivatives aren't getting way worse with each step. They're just popping out a few extra constants. So our second derivative would be big A little a is a constant. The derivative goes right through that. The derivative of cosine is negative sine little at. Then the chain rule gives us another little a. And then we get minus, the derivative passes right through the big B little b. The derivative of sine is cosine little bt. And then the chain rule derivative of that gives us another little b. So, with this cleaned up, we get what? We have a negative sign, big A little a squared sine at minus big B, we got two little b's, and then cosine bt. Okay, let's see if we can, hopefully this is enough for us to finally start making some forward progress. There's our position, we think, and its first and second derivatives. Now, what can we do with all that? At time 0, the position was 0. What does that do for us? If t is 0 here, then we get big A sine little a times 0 plus big B cosine little b times 0 equals 0. They said s is 0 at time 0. So these zeros are the times, this 0 is the position. And if we clean that up, we get a sine 0 plus b cosine 0 equals 0. Sine 0 is 0, so this whole term vanishes. Cosine 0 is 1, so we get b times 1 equals 0, which means b equals 0. So after going through all this setup, the first thing the math tells us is, oh yeah, you were wasting your time with that cosine, unfortunately. There is no cosine component to this, or the amplitude of the cosine is 0, so sad face, but it was good to keep an open mind going into this and to be ready for that cosine to happen. Now the math is saying you can dump all these everywhere that you have a big B, it's actually 0, which means for the most part you can ignore it. Our solution is just going to be a sine. So it stings a little to have spent all that time on it and not get too much, but at least it's good news because our solution is going to be nicer now. What else can we get from this? This didn't tell us anything about capital A, unfortunately. It told us capital A times 0 equals 0, which is true for any number under the sun, so we need more. And oh, look, here's more. The first derivative at time 0 is 1/2. Let's see if that can do anything for us. Here's our first derivative. It's big A little a cosine little a times the time is 0, and that's got to come out to 1/2. So we get big A little a. Cosine 0 is 1. I'm just going to get rid of that part to save a line. So big A little a equals 1/2. Okay, well that's something. I can't solve for either one of these because this is one equation with two variables in it, but that's worth remembering at least. Hopefully we can circle around and solve for this later. The last thing we have that we have not used yet is the original differential equation, which says the second derivative plus 9 times the position equals 0. Let's see if we can get anything out of that. Our second derivative is minus big A little a squared sine AT plus 9 times the original position, which is A sine AT has to equal 0. If we factor out the signs here, something interesting happens. Take out the sine AT, and we're left with minus big A little a squared plus 9 big A equals 0. So either this means the sign is 0 all the time, which is impossible, signs bounce around, or this part equals 0, which is intriguing. Let's look at that. That would mean minus big A little a squared plus 9A is 0. Divide both sides by big A. Minus A squared plus 9 equals 0. A squared equals 9. Little a is plus or minus 3. Okay, now we're getting somewhere. A is plus or minus 3. Now we can solve for little a, or sorry, big A. We can say big A is 1/2 divided by little a, 1/2 divided by 3, let's say, equals 1/6. Okay, so we've got our amplitude, we've got our frequency. This is starting to look good. By the way, you notice how I suddenly stopped talking about plus or minuses here? When you're using a frequency like this, it is customary to give this as a positive value whenever you can. If that gives you a sign that starts at the origin and increases, that tells you that you've got a positive little a value. If this value were negative, it would result in this whole thing being flipped horizontally, which would mean it drops before it rises. And I don't think we have any information that can tell us which one of those it is. So basically, I just selected the positive value because it was nicer to work with. I think that'll be enough for this problem. And if it turns out it's not, then we'll just switch and use the negative. But for now, I'm assuming the positive just to make my life easier. That's not a terrific reason, but it's the truth, and I think it's going to work out. So I'm saying that our position function is big A is 1/6, sine little a is 3t. Now, I'm going to clear out some of this work on the right and check that and just confirm that it satisfies everything it needs to. Sorry, this example is running a little long, but it gets a little gory when you've got all this trig and all these derivatives. So if that's our original function, then its first derivative would be 1/6 cosine 3t times another 3. So 3 out of 6, that's 1/2 cosine 3t. And its second derivative would be, from cosine we're going to get negative sine, and then another 3 is going to pop out. So it's going to be minus 3 over 2 sine 3t. So when the time is 0, we're going to get sine of 0, which is 0, which means our position is 0. So this requirement checks out. When the time is 0, the first derivative, s of t, is going to be 1/2 cosine 0, which is indeed 1/2. So we've got our first derivative requirement. And the last thing to check is if we do our second derivative plus 9 times our original function. So if we have minus 3 over 2 sine 3t plus 9 times 1/6 sine 3t, that should all come out to 0, does it? Minus 3 over 2 sine 3t plus 9 over 6 reduces to 3 over 2 sine 3t. Yeah, it does indeed equal 0, so it all worked out. This is our position function. This is the equation for how that pendulum will swing.